Okay, we've talked about it earlier. In a way, we talked about zero force members. So, of course, that means that there are going to be certain members that have no force in them. How can we recognize them quickly, at least some of them or most of them quickly? If we look at a free body diagram like this one, which is the free body diagram at this node F, and let's just say that this is what it looks like. We have an FFG, an FFE, an FFC. If I look at this free body diagram and then I take the sum of the forces in the y direction equaling 0, I'm going to see, since these two are horizontal, that we just end up with this load, which is downward, so negative, minus FFC equals 0, which of course means that FFC equals 0. Okay, so what's unusual, or how does this pop out from this free body diagram? Well, if we notice, this is a T. In other words, the joint, the node, makes a T, which means that I have two horizontal forces, but only one vertical force. And notice there's no load here. In other words, there's no 10 kips or something like that. That doesn't exist because then we no longer have a T. Okay, so I have to take into account the load as well. But what I'm showing here is a node with no external load, that's acting in a vertical direction. And so that becomes a T. And simply because we can take this sum of the forces in the y direction equaling 0, I'm going to end up with this load being 0. So if we have a T shape for our free body diagram, so a T, now I'm just going to tell you, so it could look like this, but same thing applies if it's upside down, or if it's sideways that way or sideways that way. So any of those cases are going to give me that the stem of the T, so this part, this part, this part, this part, the stem of the T is going to have 0 force. In other words, if I'm looking at this, what do? I take the sum of the forces in the x direction equals 0, and I get that this member will have 0 force. So we can identify, when we look at our truss, we can identify 0 force members by looking for this T. Now, what happens if the T is distorted and it looks like this? Well, let's figure that one out. Let's just say that, so let's look at this free body diagram. And in this case, I have FFB here at an angle of 60 degrees. I take the sum of the forces in the y direction equaling 0 again. None of these contribute. So I have, this heading downward, so we should be able to do this now without, drawing more diagrams. I'm going to have minus FFB sine 60 equals 0. Well, what happens? I still get FFB equals 0. So what we find is this is another form of a T. It's a distorted T, but still the stem of the T gives us a 0 force member. So, and again, we can rotate this so I can have this T, I can have this T, I can flip it upside down and be like that, flip it upside down, be like that. It can be sideways like that, sideways like that, or like that, or like that. And it can be like that. So, in other words, I can rotate my x and y axes to look like that, and I still get the stem of the T for this one too, the stem of the T, or this, and there are other orientations and things like that. The stem of the T in each one of these is going to have zero force. And like I say, you have to take into account the load as well. But in other words, you don't want to, in other words, if a load is applied there, then it may no longer be a T. So what we're looking at is two collinear forces and one non-collinear force. So what do I mean by that? In other words, these two are collinear, that's non-collinear. These two are collinear, that's not collinear. So it's the one that is not collinear. This is the zero force member. All right, what happens if we have an L shape? Looks like this. Then I have these forces. Well, now what happens? Well, I can look at this and I take the sum of the forces in the y direction equals 0, and I get FAC equals 0. If I take the sum of the forces, I'm looking at this again, I take the sum of the forces in the x direction equals 0, I get FAB equals 0. So if I have an L like that, then both members have a zero force. And this L can look like this, it can look like this, it can look like this, it can look like this. But then similarly, what happens if my L is distorted like that? Well, what happens with the sum of the forces in the y direction? Well, I can see that I'm going to have, this is going to be FAC sine 60 equals 0, which means what? That FAC equals 0. So this becomes 0. And then what? Then if I take the sum of the forces in the x direction, I'm going to have FAB plus FAC cosine 60 equals 0. But FAC is already 0, so FAB becomes 0. So again, even though I have a distorted L, both members are zero force members. So it's about an L and a T. So L and T. Looking for, if we have an L, both members are 0. Have zero force. If I have a T, then just the stem of the T has a zero force. Okay, so you need to apply this. So this is a little homework here. Do this problem. All you have, very simple, no calculations involved. Just list the zero force members, which means you look for the T's and the L's. So pause the video here and find the zero force members. Okay, so what do we have? Here's our drawing. Now, it's a good idea to put the forces on for these, and if we look at those, we're going to see that we have an X and a Y because that's a hinge. I only have a Y here, but put those on there because sometimes they have an impact on the problem. So I'm going to look at this. We don't necessarily have to come up with the values. Now, occasionally, sometimes one of these can be 0. For instance, maybe that one ends up to be 0 if all the external loads are vertical, then that may end up being 0. So if you see an obvious 0 reaction, you should sort of take that into consideration when you draw this. But for the time being, we're just going to show that these exist and their line of action, and we're looking for L's and T's. Well, what do I see? I see there's an L right there. There's a T there. There's a T there. There's a T there. There's an L there. So let's look at then what, if those are L's and T's, there's my L, and that means what? This one, these double tick marks right here indicate zero force. So I have a zero force member here, zero force member here. Both of them are 0. For this T, it's the stem of the T that is 0. For this T, the stem of the T is 0. For this T, the stem of the T is 0. For this L, both of these are 0. Now, what does that mean? I have these as zero force members, so those are those listed. If they're zero force members, I can remove them. So let's remove them. Now, in a real truss, we don't do that because these things are for stability and for other loading conditions and things like that. But for this analysis, we can do this. So I remove all the zero force members and I end up with this. And now I look again, did I create any more? Did I create any L's or T's? This is not an L or T, this is not. You just look at all the nodes. So none of them are L's or T's. So I've created this truss, but in reality, for this loading condition, it really just acts like this. So okay, so do this one. List the zero force members for this one. So pause the video. Okay, so notice this is not a T. Why? Because I have the 20 kip load there. It's not a T. It may look like a T, but it's not a T. But what T's do we have? Well, we've got a T here. And notice we've put on the reaction here. That reaction is horizontal, which means that this is a T. I've got to take into account that reaction there. This reaction has 2. And then over here, I have an L. So for the T's, it's the stems that have zero forces. For the L's, it's both. We have zero forces. So I can get rid of the zero force members. And then, now what happens? So I remove these, and I remove that, and that gives me this. So now I'm going to look at this, and what do I see? Oh, this becomes a T. Like I say, I have to take into account this load here, but that becomes a T that was not obvious until we remove those 2 members. And that means that this member is a zero force member. Now notice it's in contrast. When I look here, you might have the tendency to think, oh, here's a T, and that means this member is zero force member. Well, it's not. It ends up that this one is the zero force member. So it's not totally obvious until you draw out the sketch. So this becomes a zero force member. Now we remove that, and we come up with this. And do we have any more L's or T's? We look at each and every joint. Is that an L or a T? No. Is that? No. It's that? No. Is that? No. So we look at each and every one when we're all done just to make sure. And notice that some of these, when we do that and simplify the truss to come up with something like this, we can immediately see some of the member forces. For instance, this is obviously 20 kips in compression. This is obviously the same as whatever that is, whatever that ends up to be in compression. So, or well, depending on what direction this ends up to be. But you can start to, there's certain things that will pop out once you simplify it. Okay, so another homework. list the zero force members here. Okay, pause the video and do that one. All right, so this one, what happens? So I'm going to look, so here I have this, let's start with the obvious ones. That's an L, so that means that one and that one are zero force. Now I come along and I look at this and I see a T here. So if this is a T, then what do I do? Then, so basically I can start removing these just to see what these are like. So I remove this, oops. I remove that, and then I remove this. Well, when I remove the one I just did, then what? Now I have a T. I have a T there, and this now is zero, so I remove that. Then I have a T here, so this becomes zero, I remove that. So I put that, so now I'm down to this, and what do I see? Well, now I have a T here, which means this is zero force, and I have a T here, which means this is zero force, and then, so I can remove these, and then these two become zero force. And then all I'm left with is this. So that one got rid of everything. And I basically just have one member here, and it has compression of 30 kips. So this is an extreme case, obviously. And if you started to look at this, you would see, if you looked at this, you would see that these two reactions are zero. You can also, so if something comes from that. In other words, if I take moments about this point, that's got to be zero. And if I take the sum of the forces in the x direction, that's got to be zero. So another way to do it. But in this particular case, we've reduced. So we show this, but under this loading condition, it not obvious, but this is the only member that is loaded. Everything else does nothing under this loading condition for this. So we'll go back to this whole thing. The only thing that's doing anything is that. Now, of course, in the real truss, we would never get rid of all this and just leave this one, because that's clearly not stable. It's clearly not stable, but in essence, it does show that for this truss and everything being perfect and lining up, that the only member that is loaded is this member right there. Okay, so do homework. Find the reactions and all zero force members. And I want you to use just one cut, one free body diagram after that, once you've found the reactions, to find FCD, FDL, and FLK. Okay, so go ahead, find the reactions here, find the zero force members, and then use one cut and one free body diagram to get all of those. So pause the video here. Okay, so I'm not going to dwell on this, but you should all be able to get the reactions at this point. I take some of the moments about A. So I'm taking moments about here. I have, 5 times 5, 5 times 10, 10 times 8, 10 times 16. All those are positive. Minus IY times 32. I get Iy is 9.84. Take moments about I. I have 5 times 5, 5 times 10. It ends up being negative 10 times 16, negative 10 times 24. And then AY plus times 32. Should be able to do that reasonably quickly now. We get that for AY. Take the sum of the forces in the x direction equaling 0. I only have those. So AX is negative 10. So I now have my final free body diagram here. So I show my reactions. And now I'm going to look for L's and T's. And in this particular case, all we have are, I have a T here. I have to take that into account. I have a T here. So with those, what we find is this member is a zero force member. This member is a zero force member. And that's it on this one. I want to do one free body diagram, so I'm going to take this one. It cuts all 3 of the members we want cut. So the whole key is, remember, we have to cut the members that we want to find the force in. So that's those 3. Again, I do a copy and paste here. I guess I can show it just, to remind you. I do a copy following this exactly. Copy, paste. Just look down here. That's what I look at, and then I put forces at every location where I made a cut there, made a cut there, made a cut there. So I show those forces, and that gives me this. So I now have this free body diagram. I want to find these unknown forces. I can take moments about this point, which eliminates these 2. And I'm not going to go, you can all do this at this stage. So that's the equation that I get for moments about L. Then what? Then I can take moments about this point, about D. It eliminates these 2. Give me that equation. And I find FLK. And then I can take, I want to get this one, I can simply take the sum of the forces in the y direction equals 0. And I get that one. Here's my final free body diagram for that. More homework. So here, by observation, find these forces. Okay, so you don't even need to do it. I don't want you to do any calculations to find the forces in these members using this same truss, but now the reactions are there, and then I've eliminated. Notice I've eliminated the zero force members here. So, okay, so I want you to do these by observations, and then again, I want you to do one cut, one free body diagram, and find these forces, EF, FEF, FFK, FKJ. FEF, FFK, and FKJ. Those 3. Okay, pause the video and do that. Okay, so let's look at these one at a time. FBL. Well, FBL is right here. Well, what do I see? Oh, this is easy because these 2 are only in the y direction. That's in the x direction. So this member right here must be in compression 5 kips to resist that force. Then FEK, it's right here, same sort of thing. These are in the X direction, this is in the Y direction, so I have to have 10 kips compression there. 10 kips. FHI and FHI and FHG, well, that I can see what? This is 9.84, so this has got to be in compression 9.84. This has got to be in compression 9.84. So both of those are negative 9.84. Use one cut, one free body diagram. Well, it's going to be this free body diagram. Why? Because it cuts through all three of the ones that I'm interested in. I draw this free body diagram, and again, what do? Well, we can take moments about F, immediately gives us this. Using this expression, I'm going to let you go through that. We have our theta, by the way, is arctangent of 5/8, so this theta is 32 degrees. And then what else I can take moments about K. That gets rid of these two, and I can find FEF. Again, you can do this. I get this value for that. And then I want to get this one. Well, I take the sum of the forces in the Y direction. And again, you should be able to do this. I've got that going in the Y direction. I got that going in the Y direction, so I only have to use those two. I get that for my FFK. This is positive, so it's tension going away from the point, positive tension. This is negative, so it's going toward the point. So this is compression toward the point. Tension away, tension away. Again, some homework here using this final free body diagram here and here, sorry. These two free body diagrams. And just observation, find FDE. Okay, so whereas FDE is here, so use observation to find FDE. No calculations, just look at what I have here and then the way this is set up here. And then I want an FBD just around node F and find FFG, FJ. So around node F, F is right here. Use the information that we have. Notice we have some information here. But now we want to get FFG, this one, and FFJ, this one. In other words, I already have I have this one, I have this one. I want to know the other ones just by taking a free body diagram about point F. So pause the video and do that. Okay, so just observation, find FDE. Okay, well, what do I know? FEF is 31.49 in compression. So if I'm going to draw a free body diagram about point E, what's it going to look like? This is 31.49 in compression, which means what? When I draw the free body diagram about point E, it's got to be in compression 31.49. These two are both vertical. We've already determined what this one was, what EK was. We said by observation is 10 kips. And so all that's left is this one. It's got to oppose this 31.49. So its FDE is going to be 31.49 in compression. FDE is negative 31.49 kips. And then our free body diagram around F is going to look like this. I'm going to put on the values that I already know, those two. So I got 18.6 kips, I got 31.49 kips, and I have the two forces for the other ones. And then what do? I look at this, I take the sum of the forces in the y direction equals 0. I take the sum of the forces in the x direction equals 0. You can read these, pause the video and read that to understand it, and then I get these values. Okay, homework for this one. Look for the zero force members, find the reactions, find FED. So we want the reactions here, and ED member is there. We want that. Look for the zero force members first. Okay, pause the video and do this one. And so the zero force members, what do we have? We have a T here. We have a T here. We have an L here. So those are the obvious ones. So now I remove them. In other words, I remove the zero force members from that, and those are the zero force members, of course, are that's a zero force member. Oops. That's a zero force member. These two are zero force members. So I remove those, and when I remove those, I get this. And then what do I see when I get done? Oh, there's another T there that wasn't obvious. And that means that this is a zero force member as well. So that gives me, I remove that, I'm left with a truss that looks like that. You can get the reactions, so I'm not going to, we've done that a million times, so please read through that to get those reactions. And now we want to get, the last thing we need to do is get FED. So I make this cut, I guess I didn't show it here. I need to make a cut that will free up ED. And then once I do that, then I notice that this is horizontal, this is horizontal. So if I take the sum of the forces in the y direction, I'm going to very quickly get FED. So I simply look at this, and I take the sum of the forces in the y direction equals 0. My theta is 51.3, so you can look at that. And then I simply this has no impact on the equation, this has no impact on the equation. So all I have going in the vertical direction are this, this, and this. Use the sine of theta, FED sine theta, plus 25.9 plus 20. Solve for FED, I get negative 58.8. And another one, again, find the reactions. You should be getting, I'm making you do this simply because it's necessary to get really good at this, and the more you do this, the better you are. Of course, these, use cosine and sine, cosine and sine, cosine and sine. So find FBF, FDF, FCD, BF, DF, CD. Should give you some ideas on how to do this free body diagram to find those. The reactions, I'm going to let you read these to get the reactions. And these are all obviously x and y components at those locations. And we end up with a final free body diagram that looks like this. I'm going to take this free body diagram because it cuts through all those members that we want. I copy and can use copy and paste, whatever. I end up with that. And again, what do I do here? I take moments about F. I can take moments about D. Taking moments, in other words, taking moments about F eliminates these two. Taking moments about D eliminates these two. And then I can take the sum of the forces in the y direction to get that one. So it's the same thing that we've been doing. I'm going to let you read that and get those values. This becomes then our final free body diagram. Again, we notice that's compression, tension, tension. So the compression one goes toward the point, away from the node, away from the node. It's final free body diagram there. Okay, I'm going to pause there.